top of the hour.
Okay. Okay, Holger.
No, let me say, this is a NASA presentation. I imagine you're recording this for academic purpose, not for commercial purposes, right?
That's right. It's just being recorded for our students.
I should have confirmed with you. The purpose is to put it on our website so that it's accessible to students who may have occasional conflicts to attend, or also to anybody who wants to go back later and look at it. So if you have any proprietary material, please do let me know, and I'll stop recording.
It's not for that I'm asking you, but if when we use the NASA logo, which is here, that logo can only be used for nonprofit because cannot be associated if you are selling anything there. Okay.
Right.
That, and the reason because you pay taxes, so you already pay for this. Okay. So it cannot be paid again. Okay. So people already pay for having this, and our duty is to share this with everyone, not only in this country, but throughout the world.
I agree with that idea. I like that idea.
Yeah. For that reason, you will never see a sign of Coca-Cola and NASA at the same time, okay? Or Tesla, okay, and NASA.
All right. Well,
okay.
Our speaker today is Dr. Mario Perez, who comes to us from NASA headquarters. He got his PhD in physics from Brigham Young University as an expert in young stellar stars. He spent some time at the Goddard Space Flight Center, the European Southern Observatory, and Los Alamos National Laboratory, doing things on astrophysics and technology and space technology. And today he's going to talk to us about NASA's orbiting astrophysics or observatory program. So welcome.
Thank you. I hope you hear me well, right?
Yes.
Okay. Thank you very much for this invitation. I have to say, during the COVID time, we have received so many of this invitation because now it's very easy for us to be online in every online physics seminar and astrophysics seminar around the world. There are no constraints right now. So let me say, I want to speak for a few minutes here, and I have several biographs which I will go quickly to give you a sense of what we do. And I'm looking forward to some questions, please, at the end. Okay, so I'm going to talk about astrophysics, discovery, and the upcoming decade, okay, to give you a sense of future. Okay, my topics here, and some of them are one or two biographs, is why astrophysics? You may be wondering, because this is a physics seminar. Talk a little bit about the remarkable decade, which is the one we're finishing now. A little bit about astrophysics missions, what do we do, how many we have, and what are the plans for the future ones. About technology archives, because I'm mindful that you teach physics and you give a PhD on aeronautics and engineering, and you may be interested in our technology. So also the role of technology in our job here, some challenges, emerging technologies, and you may ask at the end how it can help these people, us, and we will ask you to join us. Okay, why astrophysics? And here we have the three important questions that really give the rise to three different programs we have in astrophysics here. The first one, how did our universe begin and evolve? That is called physics of the cosmos. The next one, how did galaxies start and planets come to be, which is cosmic origin of the origin of the universe, and are we alone? Which is probably the most compelling question that everyone is asking. All three questions feel like they're religious questions, okay? How we're here, right? Where are we going? Are we alone? And how we came about. And there are, in fact, there are very, very important questions that not only for astrophysics, but really for history, for philosophy, and certainly which what we call cosmology in the old days. Now cosmology become a mathematical discipline, part of astrophysics. And I want to mention here the documents that we have on the bottom. Those are decadal surveys. And we have an astrophysics 5 of them. In fact, I'm going to click here and we will have one more, number 6, next year. Around the spring, we will have one from the National Academy of Science giving us recommendation to do in the next decade. So here, why astrophysics so unique? I'm going to say that astrophysics addresses the most difficult and profound questions, which is the question that I just mentioned to you about the nature and origin of the universe and then seeking life outside our solar system. So astrophysics, at least NASA astrophysics, quite ambitious, and those are the answers we're trying to seek. On the other hand, astrophysics is a photon star discipline, demanding exquisite performance from all system and subsystem utilizing on sky observation and detection. So here we have a dilemma. We're trying to answer the most important questions on one hand, and on the other hand, we have very little to play with because we're trying to look for very faint object, very weak, very distant, and we don't have a lot of photon to work with. So here I'm going to mention that all the information that we use within astrophysics is all public. All of this document you see here are all public. And I want to, if people are here from history or history of science or interest in planning and strategic decision making, this is a great field to look into because all of this strategic plan that we have from the agency, from the National Academy of Science, which are this column here, and for the one that we have come as the implementation, are all public and they're part of the record that people can download. I mentioned that we do have this guiding document. Now, what about the decade? I said I will talk about the decade. We are experiencing a remarkable decade, and I know 2010, 2020, I have 11 years. I know that the physics people and the mathematics people are going to say, hey, you have 11 years there. And I do have 11 years on purpose, okay? So we started with the 2011 Nobel Prize for Dark Energy and Expansion of the Universe. We had done discovery a lot of new exoplanets in this decade, especially with a mission called Kepler. I'm the program scientist for Kepler, and we just finished that mission at the end of September, in fact, last month. Flew for, I think, 2009 for almost 10 years. We have seen a resurrection of astrophysics and asteroseismology, advances in galaxy archaeology, a better understanding of our interstellar medium and circumstellar galactic medium. The decade continues. In 2015, was awarded again the Nobel Prize for neutrino oscillation that are very important for neutrino science, and it had an implication with the mass of neutrinos. We saw a lot of important advances of active galactic nuclei and physics, their physics, cosmic web, large-scale cosmology. Gravitational waves were discovered, right, on February 11, 2016. And from that on, we have seen many, many detections since then. There was a great American eclipse, right, on 2017 that 100 million people participated in this country, okay? But in 2017, we have yet another Nobel Prize, in physics on gravitational wave detection, which was done the year earlier. But the decade continued. 2019, again, was a Nobel Prize in physics for astrophysics for the contribution to our understanding of the evolution of the universe and Earth's place in the cosmos. This was done for cosmology and also the discovery of exoplanet, which was given to 2 Swiss astronomers for the discovery of 51 Peg. And back-to-back Nobel Prizes a few weeks ago, right? 2020, the Nobel Prize was given again in astrophysics for discovery that black hole formation is a robust prediction of the general theory of relativity. So we are Out in this decade, 5 Nobel Prizes start 2011 have been given to astrophysics. So we're experiencing a golden era for space astrophysics and ground too. We had the great observatories like Hubble, Spitzer, and Chandra still operating. Chandra, in fact, I had to say, Spitzer to say was finished early this year though. But during the decade they were operating, and we have 17, up to 17 missions during this decade. Now we had 9 operating and 10 missions in development. So we do have good future, but right now we're going through somewhat a minimum for many reasons. What I explained. Okay, I had to mention of the mission that are gonna be flying next year. This is the mission of missions, okay? Very expensive one. Webb is the largest one that NASA had ever built. It's the official budget is way over around $8 billion, if not $9 billion. But it's large. This is a 6.5 meter diameter telescope that you see in the illustration here. And it's gonna give us a light into the beginning of the universe. Okay, this is it's an infrared mission, and expected to fly in October, a year from now, in October 2021. People have been kind of skeptical about this mission because it's expensive and always have been 2 years away. Okay, but now it's 1 year away. Okay, so that's comforting. Okay, the great observatories here. What we're doing in the future is really to also have access to many wavelengths. And this mission, W1, which is called Roman now, and was named under Grace Roman, which is one of the female astrophysicists here at NASA. This Roman mission is going to be indivisible. It's going to fly in 2025. Webb next year, 2021, and Hubble have been flying since April 1990. Okay, so Hubble is a small 2.4 meter, but Roman is also 2.4 meter, but it's 10 times better and 10 times the Hubble field, as you can see here. So great observatory, we're planning to get to the beginning of the universe with this fleet and many others that we're planning. Well, let me go quickly about how proud we are of the Nobel Prizes that have been given in physics for astrophysical activities. The first one was, I had to mention, this is not the one that I mentioned, but I had to sneak it here because it was given to an NASA employee. And this is to Dr. John C. Mather, got in 2006 for the discovery of the black body form and anisotropy of the cosmic microwave background radiation. He's a very tall fellow. You can see here, like more than 6, almost 7 feet tall. So it's a huge fellow, very smart and very nice individual that he still is employed by NASA and is one of our colleagues here. 2011, I'm gonna mention quickly here, this is the 3 people that got the Nobel Prize. All 3 working with supernova activities and using from the ground and from space using Hubble. This is Sol Mitter, Adam Rees, and Brian Schmidt. The next one, 2015, I mentioned, this was given to a Japanese professor and Canadian researcher, Arthur B. MacDonald, okay, for finding the oscillation in the neutrino. The next one, 2017, was given to 3, this was all American Nobel Prize given to 2 professors at Caltech, Barry Darich and Kip Thorne, and to an MIT researcher there, Rainer Weiss. Impressive achievement. Then 2019, given to James Peebles from Princeton for doing to bring cosmology into the area of precision cosmology. And Michael Mayor and Didier Queloz from Geneva University sharing the prize for discovering the first exoplanet of this decade, well, of this modern time. By now, we have about 3,500, 4,000 planets. So now if you discover one, you don't get a Nobel Prize like they did, okay? That was the first one, the most difficult one. And just 2 weeks ago, a week and a half ago, the Nobel Prize in 2020 was given to Roger Penrose from Oxford University for the theoretical work he did in cosmology and the prediction of black holes, and to two observers, Reinhard Wenzel from Max Planck Institute in Germany, and Andrea Guess from UCLA, okay? And she used Keck. I'm also the program scientist for Keck, so I'm very proud of what she did at Keck Observatory in Hawaii. NASA doesn't own Keck, but we are partnered with Keck Foundation there, okay? Okay, a little bit about missions now. You may be saying how many missions we have here, the science fleet. And here we have the galaxy. If you can see here, I can see my cursor here, the galaxy. These are the astrophysics missions. Around the sun, you have the heliophysics missions. Around planet here, you have the planetary missions, right? And around the Earth, you have all the Earth science missions, which are the 4 science directorates. We do have another one now called biological and physical, which is the one that manages the space station, and they do experiment too. So we have 5 science divisions within NASA. Astrophysics is one of them. So if you're interested in another aspect, you can also ask people from either heliophysics, planetary, or biological and physical science, or earth science to give you a talk and explain their fleet and their activities. So this is a portfolio of about $6 billion a year, and we have over 100 missions. Flying and in development. Not all of them are flying, but about 100 over 100 spacecraft in the sky right now. This is not a lot because already Starlink has more satellite than us. So we're not the bigger player right now because the mega constellation are going to have few thousand, 48,000 OneWeb will have. So we're going to be very, very small. But we were big at one point. So astrophysics mission operation, just to review them, all the first row here, they're all in operation. The most ancient one, Hubble, as I said, it started in April 1990. And we had Chandra, XMM Newton with ESA, Gerald Swift, that's a NASA mission, Fermi, Noon Star, which is a small mission called SMAX, Sophia, it's an airplane, it's 747, which started operation August 17th. It's the only one affected by COVID, by the way. All the other ones, since they were flying, they were unaffected by the pandemic. We have one in the space station, ISS NICER. And we have a mission test that has discovered most of the exoplanet lately. So this mission replaced Kepler, okay? And then we have 3 other programs, the balloon program, which was suspended for obvious reasons, but we launched balloon in Australia, and New Zealand, and New Mexico, for summer in New Mexico, and Palestine, Texas, and in the Antarctica as well. Sounding rocket, we do also have a program on sounding rocket for astrophysics, and I started launching in September 8 again. Very active program. We do manage archives around the country. So we do have at least about 6 archives, and those are being operated nominally. Okay, mission and development. This is about the future. We have, as I mentioned, these are all missions. These are all 10 missions here. So Webb, and then we have XP, Gusto as a balloon. I won't spend a lot of time explaining them, but we do have a lot of missions. Okay, Roman is the one that I mentioned called WFIRST in 2025, Nancy Grace Roman Space Telescope. The one that we're most excited about, Webb here. The other one are kind of small, these 3. Euclid is a big ESA-led mission, okay? That is going to be very similar to Roman. And the Phoenix, one that managed by Caltech, is an all-sky infrared mission. And then we're making a decision of whether this is going to be COSI or SCAPE. COSI is from Goddard and SCAPE is from University of Colorado, or in this Dorado is the Goddard one, and LEAP, I believe, is University of California. So these are 10 missions that are in the portfolio in which we're in development. They're all advancing and hopefully start being launched next year. Next year, we have 3 launches here, which is good. But we also, since 2016, we study 4 other missions. And these are the future missions, especially the young people that are listening to me here. When they're my age, they're going to see this mission. This is going to be their Hubble for their time, okay? One is called HAVEX here. This is to discover exoplanets. This is either 4-meter diameter mission. LUVOIR is the largest one. LUVOIR is a large ultraviolet near infrared. And this is about either in a version of 9 meters or 8 meters, sorry, and 15 meters. These are large ones. And then LYNX, this is an X-ray mission that will study, and Origins, that is an infrared mission. That's a cool infrared mission, okay? If you're interested in following this, I have the website. I hope you can see them on the bottom here, where all these reports for this mission have been made public. So if anyone is interested in following this mission and getting involved, and I have ways you can get involved at the end of my presentation here, please download the reports. They're all public. And as I said, for being from NASA, you already pay for it. Now, I want to say that all what we do is really public. So we have the integrated strategic technology portfolio. And in 2018, we do this every 2 years. So the next one is going to be in 2021. We published the Astrophysics Biennial Technology Report called ABTR. It also public. Here are the website where people can download them. And here are all the projects that we have funded through NASA. Like people like you, if you get any funding, you are part of our portfolio, and we track what is being done with those technology grants. So you're invited to be part of this. I don't know if Kansas here is it here in this map? Well, I hope you are there, okay? Yeah, I hope you are there with some project. Huh?
Kansas is there. You have it blue.
There, okay, excellent. Yeah, so that means you're there, but you can be there. You can be with more projects. So we have, stay there, no, they're interested in that. This is for astrophysics only, not for NASA, okay? This is for astrophysics, okay? They stay like Nevada, I see there's no working with us, okay? The rest is pretty much working. I see Utah's not there. I see Wyoming and Idaho's not there, but Montana is there because Montana, believe it or not, they worked a lot on gravitational waves, okay? Okay, so, okay. And the technology here, which I just mentioned, we do have all the technology that we had done. It can be, and these are the technology type, cooling system, coronagraph, detector, you can track what have been funded. So if you wanna join us, don't do what others are doing, but do something beyond of what others are doing. And this is public, okay? So it's not even a NASA website, so it's .us, okay? So it's good that you can see what are we involved, and this is technology, and this is electronics, optics, material science, as applied to astrophysics. So welcome to see this. This is, again, for the public to check them out. Now, if you ask me, when we studied the 4 large missions, we came with technology gaps, okay? Meaning something we need to work on. So if you ask me what I'm interested, here's a list: priority 1, 2, and 3. I know this is kind of a nice chart. Hopefully you are close to your screen since I'm not projecting, you can get close to your screen and read there what we want. For example, detectors is a big issue. Coatings, detectors, optics, cryocoolers, for example, adaptive optics, deformable mirror, for example. Big technology gap is stability, okay? We need to look for new material that are more stable under very stringent physical conditions. Mirror segment, anyway, any of this could be a good dissertation topic for any of you, or even senior project if you wanna get involved. But these are the missions that need this here in the fourth column. And the third column is the type of wavelength that is applied to, in the last column, okay, sorry. It's the page where this is referred to in the document called ABTR, Avatar 2019. So we didn't have this some time ago, that we didn't know what we needed. Now we do know what we need, okay? Because the community had come together for 3 years and had told us, for the large mission we want to do, these are technology gaps. This is what we don't have. So we need to retire these gaps. Okay, now I'm going to talk a few challenges, okay? First one is large cost of astrophysics missions. And these are, quote, this is my director, Paul Hertz. And he said it in 2013 for the first time, but I've been repeating this since then, okay, for 7 years. I'm not interested in estimating the position of the cost of future astrophysics mission and instrumentation. I'm only interested in lowering their cost. So this is what we need to, okay? We don't want more studies of how expensive our missions are, but we need really to lower the cost of our mission. And our NASA Associate Administrator for Science have been repeating this since 2018. Why astrophysics flagship, meaning the large mission of astrophysics, why are so expensive? Because in applied data science, they're $1 billion, maybe $2 billion. And why in astrophysics, they're $8 billion. You know, in earth science, everything is cheaper than $1 billion, okay? Well, one reason is that they only had to fly around the earth, right? We always had to fly distant, and we have many more challenges. And that's a reason, but it's still, we need to, that's a reason, but it's not convincing to even Congress, okay? So we really, that's a challenge. The next challenge, the connection of observation, astrophysics, and technology. If I'm talking about technology, you may say, hey, the main problem you may have, they're all astrophysics in nature. And the answer is no, really. And I'm gonna say this quote here, which is mine: groundbreaking discovery in astrophysics are directly related to advancement in technology. And many people have said this before me and after me. So the corollary of this, a lack of investment in technology, will impact negatively science achievement. So we really, our needs are in, at least for observational astrophysics, are in technology. And I want to even quote a royal opinion here by Sir Martin Rees, which is the UK astronomer royal, because if you're an astronomer and live in a country with a king or queen, you can be a royal astronomer like he is, okay? He's part of the court. And he said, I'm going to quote him in a book he published last year, and I attended when he gave the talk of this book. And he said, but it's important to emphasize that progress will continue to depend, as it has up till now, 95% on advancing instrument and technology, less than 5% on armchair theory, but that theory will be augmented by artificial intelligence and the ability to make simulations. And this is a fellow that is a theoretical cosmologist, okay? So he said 95% advancement will come from advanced instrument and technology, and 5% of what he does. And he said, even there, we're gonna see artificial intelligence being used. So this is a strong opinion that we really need to invest more in technology, more time in technology, because that's our bottleneck. Not have mission concept, because we have bookshelf full of mission concept, okay? All right, so what else? Another challenge here really is to the urgent need of innovation and better practices. For astrophysics, okay? I said here, an effort of lowering the cost of space mission innovation is not an option. It's required to break the current paradigm of practices and status quo. So innovation for astrophysics is not like, I will be nice to have it, but really is a mandate. Innovation initiatives should be a unifying focused effort by academia, industry, and government laboratory. And I'm going to quote this quote by Dr. Wirtz, which has several publications, right, on missions in general, mission and space mission cost. He said, for a great many space missions, we should be able to reduce cost by a factor of 5 to 10 while maintaining higher reliability and reducing fragility and vulnerability. If instead we continue with business as usual, we simply don't have enough money to do the things that we need to do and want to do in space. And this is pretty much what have been said for a lot of things in space. It applies particularly well in astrophysics, okay? Astrophysics, if the next mission is won't be $9 billion or 8, like it's Webb, it's gonna be 20, it's gonna take us too many years, maybe 2-3 decades to do it. And soon we will have not enough money in the national budget to do one mission. So we need to really cut into doing things different way. And I have a quote here that I like to say when I talk about innovation: the electric light bulb did not come from continuous improvement of candles. And now I should update this because incandescent light, right, or LED light now didn't come, okay, of continuous improvement of incandescent light. So in fact, we do have a next generation of illumination, which LED, that is completely different from incandescent light. So this is innovation is disruptive and really it's not predictable sometimes. It's not continuing what we are doing as usual, and that's what we need to do in astrophysics. So what have we had done with this mission technology gaps and the fact that we're more aware of this? So here at NASA, in the last 5 years, we have learned and understood that these technology gaps are the obstacle to implement, build, test, and launch future large missions. And the program that I have at the bottom here, okay, is something that we have started in the last decade and a little bit longer. But I had to say that understanding technology development, technology inception and technology maturation, it's important how much money you dedicate to one or the other. And it's something we have been learning in the last decade only. So we have this program called Strategic Astrophysics Technology, SAT. It started in 2009. I was one of the original individuals who started this program. I was in NASA headquarters at that time. We started with technology management too, because technology is different than data analysis grants, because in data analysis of theoretical grants, you leave people alone, okay? But in technology, you need to make them part of a system, part of a community that we can use any advancement may. Doesn't have to be a full instrument, could be part of an instrument. So that with the connection of that is it need to be integrated by an appropriate management. So, and that we are doing, and we have been doing for that last decade. We are tracking milestone, technology readiness level advancement, and for all technology grants. And we started this large mission concept study in 2016, and we finished that last year. So I'm going to mention only one, because I don't have a lot of time and I would like to finish quickly here. The Promise of Astrophotonics is one of the emerging technology, astrophotonics, which, by the way, I had the first article, Physics Today, 2012, 8 years ago. Astrophotonics really had a tremendous promise, right, of reducing the size, the weight, and the power, right, of lenses, mirrors, or gratings that we use in conventional spectrograph, with optoelectronic component of using from telecommunication industry, which are the optical fibers. This will reduce mass, will reduce volume, will reduce development. We're moving from optical geometric design, right, to physical design of optical physics, okay? So this is the revolution, moving from geometric, right, to physics with optics. Astrophotonics provide that. We had given some grants. We had done some colloquiums and activities. In fact, I had a meeting this summer. We had to cancel it because it was because of the pandemic. But the full promise of astrophotonics had not been realized, in part due to only incremental advance by the community and the perception that NASA doesn't like risk. Okay, so we are trying to overcome the part that is related to NASA, which is lowering our risk, and ask the community to help us to advance this very important area in astrophysics, astrophotonics. Here I have, if you ask me, what are other emerging technology? I have here integrated photonics as the one that I just spoke about. I won't speak about small satellite technologies, and including now, most satellites may need to have their own propulsion, their own navigation system, because of the many satellite, especially small satellite, because they're going to be in a very crowded field. Now, artificial intelligence, yeah, intelligent autonomous system, but this is not the only application of artificial intelligence. It can be used for a lot of stuff, for a lot of activities within astrophysics. And quantum science in general. For astrophysics, we're interested in quantum sensing, quantum imaging, and quantum algorithm. And in material science, we're interested in novel material, metals, polymers, ceramics, metamaterial, and composite materials. So this is it. So if anyone here is interested in working with us, this is the area that we are trying to invest. We're trying to understand the risk. We're trying to come up with a strategic investment in this area, we see the future in all of them. Now, here your question, how can you help? And I'm talking here all the way from undergraduate student, graduate student, postdoc, early faculty, and deans, okay? All of them can help in certain ways. So here, the first one is a commercial, right? Commercial in the sense that I want you to join us. Volunteer to serve on a NASA peer review panel, okay? And this is mostly for postdoc. Once in a while we get a graduate student there, but a postdoc, faculty members, and everyone can serve in NASA peer review panel. So here, I won't read here, but it's gonna be good for you, good for your resume. NASA pay all your expenses. Well, not now because you do it from your home, which is boring, but when we are, hopefully next year, we invite you to a nice location and NASA pay your trip there, and you help us for 2-3 days. And this is the place to sign, okay? Sign up to be a panel reviewer. So that's number one. Number two, you can be part of the NASA advisory process. And this is mostly for senior people, for more experienced people. If you want to be informed, the first one, you can be in a mailing list and receive all information about our solicitation. Then we have 3 different PAG, which are PAG, and Program Analysis Group. One in Cosmic Origin, and this is the mailing list. One in Exoplanets, and one in Physics of the Cosmos. The 3 questions that I have 3 programs, and we do everything around those 3 activities. Okay, so we have 3 different communities here. People can be part of that. We do meetings. Everyone in the community could be part of that. Now, the NASA Astrophysics Federal Advisory Committee, we have 3 of them. Astrophysics Advisory Committee called APAC, which is the one that report to what's called NAC, NASA Advisory Committee. This is the National Academy of Science Committee on Astronomy and Astrophysics, right? And called CAA, and that's the National Academy of Science. Not everyone needs to be in the Academy of Science to participate there. And the other one called Astronomy and Astrophysics Advisory Committee, which is AAAC, which is funded by Congress. in which NASA, NSF, and Department of Energy receive advice from them. So these are, we follow their recommendations, certainly. So these are important committees to serve on. Now, you can also join us by writing a NASA proposal, okay? And people say, oh, what are your solicitations? Well, here's the list of the solicitations. This is the ROSES program, which is an omnibus announcement, which contain all of this element, not only for astrophysics, but for science, planetary science, and heliophysics. So here, supporting research and technology, we have all the solicitation. The one I put in red is the one that I'm participating, and then two of them I'm in charge. I'm in charge of the Strategic Astrophysics Technology, SAT, and the Roman Technology Fellowship. These are postdoc fellowship for people that want to become PIs, okay? So data analysis, we have all of these solicitations, mission science and instrumentation all here, and we have the guest observer or guest investigator program, which are run here for these missions. You see you have 5 and 4 more. So we have 9 of them now, in which we also provide money for people to observe from our spacecraft. Okay, so this is the ROSES, which is stand for Research Opportunity in Space and Earth Sciences 2020. This include all the solicitation that I mentioned. Since it's called ROSES, right, NASA, as a cute thing, published it on Valentine's Day, February 14, 2020. And all ROSES 2021 will be published on Valentine's Day in 2021, which is cool, okay? So go there, this is public, all this information. Now, if you're more like a computer geek and you want to do an informal thing, you can do citizen science project. NASA has at least 21 of them. I have here the website. You can Google them, Citizen Science Project, and work on your own time in your basement. And you can discover disk, exoplanet, can discover new comets, can discover abnormalities on the Earth, on the Earth's surface, all kind of cool project. And this has been very successful adventure. We have thousands and thousands of people around the world working free and from their own computer, their own internet, and mining the archive that NASA put there for free. And lastly, if you really are even a programmer, you can do a space app challenge. NASA with the Canadian Space Agency, the French Canadian Space Agency, JAXA, which is the Japanese, and ESA, the European, have one every year. And this one was just passed. But for the Space App Challenge 2021, it's on October 2nd and 3rd, 2021. And that's going to be 10 years that NASA have been doing this. And this has been very successful, okay? So this is the path forward. We do have path forward, okay? We do have future here. Hopefully, probably next decade, we will not have 5 Nobel Prizes in astrophysics. Well, we may have more. But this has been remarkable so far. We really need to keep receiving the support, right? The general support of the contribution of the US taxpayer, because I have to say all what we do is because of people paying their taxes. And NASA Discovery are not only belong to the US, but also belong to all humankind. Okay, we expect to receive Astro 2021, the decadal survey, which will give us guideline for the next decade. This is going to be given to us by the National Academy of Science. This is every decade for the last 7 decades now. We have been receiving, and that's what we do for the next decade. And let me say, astrophysics is exceptional in many ways because we're trying to answer the most important questions, which I have repeated here, right? And we're limited and certainly in the amount of information we receive from those cosmic bodies. So thank you very much, and I'm hoping you guys have some questions now.
Thank you, Mario. That was really great.
Okay, let me say, yeah, I don't have anything else, but let me say this quote that I like, that I have to conclude here. The greater danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark, Michelangelo. So like this, come and explore with us. And this is it. Thank you.
All right, thank you. Well, we got 25 participants right now. Like I said, a lot would climb in as soon as we started, which they did. It was a very exciting talk, and I'm open to questions, but I was going to take the first question. You know how it is with the person who runs the seminar. The astrophysics program has been very successful. I know that Martin Weisskopf at Marshall Space Flight Center has praised it many times. I also know that, of course, he's on the X-ray, Chandra X-ray Observatory project. I also know that the
PI of that mission, IXPE that I mentioned in development, he's the PI too of a new mission. Yeah,
that's right. And so I guess I'd like some of your advice. We've had a NIAC phase 1 and then a NIAC phase 2, which has been very supportive of getting some new ideas in our lab here started. And some of the graduate students that, or actually both of the graduate students that are on the project are online listening to this talk. And some of them have, one of them has plans to submit a NASA fellowship application with
Excellent.
the NSTGRO on some of the detector technology that the NIAC phase 1 and NIAC phase 2 are supporting. And maybe you could comment on that, but also comment on going from the NIAC program to an astrophysics support. You know, that's a big leap. And of course, the NIAC program officer told me just last week that it's actually much easier if we get a support from an agency like heliophysics or astrophysics, that they're interested in the project, but they'd like to see us apply for a NIAC.
Talk to me. You're talking to the right person, because STMD, okay, the director that has the NIAC program, normally when they receive one in astrophysics, they ask me, okay, whether we're interested, whether what we think about, and they ask us some time to get reviewer for them. So essentially, if you talk to me about that project, I can probably be better informed, okay, to provide better information to STMD, which is the directory that is the home where you are sending that proposal, okay? Yeah, I think talking to us is something that people don't do in the community, okay? And if I were you in any university, I will know who is who in this agency and talk to them, because to me, that's the best way not to waste your time, okay? If the solicitation if you download a solicitation, you call the program officer and say, hey, what about this, okay? You guys interested in this and that? Is this the year to do this or not? And people will tell you things that are not in the solicitation, okay? That give you good hints, okay? So I think that is something to be in touch with the people that are the program officers of this solicitation. It's a good thing. So it's not much as used as you would think, okay? People don't do that. They do it cold. And cold sometimes doesn't play well. You have to submit 2-3 times in order to get to know the system and then be able to be successful. But you can shorten that time, okay, doing your due diligence.
Okay, well, let's plan to have a talk someday in the future.
Yeah, and those students can send me email and say, Mario, what do you think about this? Or is this a good idea? And I have been talking to people, postdoc. I just talked to one of them from NIST. And he said, Mario, I need to talk to you about this. So I said, what are your ideas? So I said, you really need to invoke the science you're going to do, okay, for us. Not for STMD, because TMD is about all hardware. But for us, you need to, what of the gap, not technology gap, but the science gap, which I didn't show here, which one are you trying to solve? You need to allude to that and then create a plan what measurement you need to solve that. And from the measurement, go to the instrumentation, right? And the instrumentation to your design of what you're doing. And then you work how you're going to do a good work plan. Okay. So we did several things, and this fellow followed that. Okay. His proposal got very good. In fact, we're close to being excellent. And only because he talked to me and I told him, put this section in the proposal. Okay. And justified them properly. And he just listened, took note, and did it. And so he saved some, well, I saved him some years of doing and getting frustrated, okay? But normally we give this to everyone that we give, and this is not the talk that I'm giving here, but also in the future, if we can ever travel, I can go to your place and stay a day there and give a seminar about how to write a good proposal for NASA, okay? And I had done this. I had done in many universities, including University in the West. I had done to Yale University. I went like last year. I went to Yale, Gate 1, Penn State, and many other places. So yeah, when we can travel, I think will be a good thing to have people come over. And like me, there are many people in other directorate that can freely go. Since I work for NASA, there's no way you can pay me. So I have NASA pay for that. So even that is convenient for you. So.
Okay. Well, other questions from other people. We have a large audience of 23 people now. Let's see, does someone want to speak up? I see Nathan wrote something. You want to ask your question, Nathan? There's no such thing as a naive question, so go right ahead. Oh, maybe he's not there anymore.
Well, he's still logged in, but not unmuting. He's without a microphone today, so I'll ask his question for him. He's saying, in calling for advancement of technologies, how does astrophysics account or research the complexification of technological apparatus to the observer effect problems of human inquiry into our solar?
Yeah, I'm trying to read the question. It's not easy to grasp what he's asking. To me, it seems to me that he's making a connection quantum mechanics here, that whenever you have a system, right, you observe it, then you're interfering in the system, right? The observer effect. Well, let me say in general, we don't have the quantum mechanics problem in astrophysics, okay? The universe is so big that we can send very big probes, right? And missions, and we may not be affecting we may not have the observer effect problem, okay? When we're doing smaller things, yes, you change the system by observing it. But in astrophysics, that's not part of our problem, okay? I don't know if I understand that correctly, but yeah, he can elaborate a little bit more in the chat. I can read it, so.
Okay. All right, so there's a hand raised by Professor Umball. You want to go ahead and talk?
Yes, thank you very much for such a nice talk. I have a question regarding the quantum sensing you mentioned. Can you elaborate a little bit more that what NASA is interested in that topic?
Yeah. Right now, in fact, what we observe, and this was said by a fellow that is an expert on quantum sensing, what we observe the flags of, let's say, a star or galaxy, okay? The flux is an integrated quantity, right? That it really is like the scalar of what we're observing, right? Is the amount of energy that we receive on a detector, on the focal plane of the detector, okay? And that all our instrumentation is based on flux detection, okay, on flux levels. But in quantum, there are they are the imaginary component, okay, that we don't use, okay? And that had to do with polarization, okay? That had to do with the timing, right? The position of that photon, the timing, and also the quantum signature of that photon, okay? So essentially, right now, we're in astrophysics, we're using the simple way of doing detection. And all astrophysical detectors are based on flux, or I would say, the scalar component of this very complicated wave, right? So in the fact that we are not using polarization or right or left hand, we're not using interference, we're not using superposition, we're not using any of the quantum phenomena, right? With this photon that arrived to a focal plane, we're losing that information, okay? So quantum sensing for us is moving from the detector that just detect one aspect, which is the intensity of the photon, right? That are deposited on the focal plane. We need to use these other parameters, right? Which will require far more, more complex detectors, okay, for us to detect. But quantum sensing, if we can make sense out of what we can use, quantum sense is interesting. It's good for photons, limited circumstances, so astrophysics is okay, but it's not when you have one photon only. You need more for statistical purposes, okay? So it's interesting that astrophysics is at the edge of using quantum sensing because, for example, heliophysics observed the sun, but they had way too many photons, right? They don't need any other help, okay? They don't need quantum sensing, heliophysics, because the Earth science observes the Earth, and if you don't get enough photon, you get closer, right? So Earth science is not the one. So planetary science, they observe planets, and us are the one that maybe quantum sensing makes sense, because you need few photons, you need quantum counting devices, but you don't need one. You need some, but you don't need a million, because I think you're overkilling, okay? But you need few. So astrophysics is at the limit that can be probably the most beneficial, okay, of the science that we do at NASA with quantum sensing, okay, from that point of view. So, but also we want algorithm, and we want quantum imaging, okay? Quantum imaging is something also that we're kind of interested in because applied to astrophysics, okay? So there are people already writing papers and working on this. If you are interested in the field, there are people doing some advancement at Caltech. JPL, for example, is a good place to go and see what they're doing, okay? And quantum sensing, quantum imaging. But we have an interest in exploring that. For example, we are not talking about here quantum communications. Okay, quantum keys, all of that. Yeah, NASA used that, but that's not what astrophysics want to pay for. Okay, that is a different part. That's called SCAN, the Space and Communication Network of NASA. Quantum communication, quantum computing, it's something beyond that. But quantum imaging and quantum sensing and quantum algorithm are the ones that are related to astrophysics, and that's what we would like to understand the capabilities and see what we can do better with better detectors in the future. Okay, I don't know if I answered your question, but we don't have a real answer yet, even ourselves.
That's good. That's clarified quite a bit. Thank you.
But get involved. I mean, a student, you have a student, those are smart kids. Give them some homework and even writing reviews on what has been done is useful. Okay, people can, yeah, in order to understand where are the limits. I didn't show you the technology gaps on quantum, okay, but we have done some of that. It's not public yet, trying to understand what is an event in quantum and what is not, okay? Because there are activity in quantum that they don't give you much, okay? But there are information you can get that you cannot get with classical detection technologies.
True.
All right. Thank you very much. Other questions?
Yeah, I have more time. If any of the kids or the student want to keep talking here, he clarified the question.
Right, so this is Nathan Philbert again writing in the chat. Let me read it to those who can't have the chat open later on in the recording. Thank you. Yes, it's the idea of developing human technologies to investigate, sense astrophysical phenomena. But each technological innovation complexifies and reduces question mark in parentheses, astrophysical phenomena to our scales of measurement, hence the observation effect. But much that I read indicates we are taking readings or measurements of the astrophysical phenomena itself. It seems we might be ways further censoring the phenomena via complexified technological sensors. Needn't take more discussion time, just attempting to state the question further.
Wow.
Thank you.
Yeah. No, it seems to me that I would say to Nathan, okay, we're in the area of astrophysics, we're doing brute force right now, okay? We're doing what we can, okay, from the platform that we have, okay? I think his question is very sophisticated, okay, in the sense that he even questioned whether we are really observing astrophysical phenomena because we're using a scale measurement or a scale of instrument that are human possible. Yes, we may not be seeing the actual universe at work here because we do have limitation of size, collecting aperture, right? But that now might be a problem in the future. I mean, when we can put another telescope on the moon, with one on the Earth, we can do interferometry, and the baseline is going to be this million of miles. Okay, so yes, as we increase our baseline in terms of measurement, we're going to be able to capture the actual universe. Yes, and that's still in the future. Right now, Hubble at 2.4 meter, right? 2.4 meter, and now Webb is going to launch next year 6.5 meter. So it's about 3 times bigger, but it's about 9 times because of the surface that matter, right? Which is square. So it's about 9, 10 times bigger. So we're moving there, but we need to go 100 times, 1,000 times, million times, but that's in the future. And for that, I would say we need the taxpayer to support us more, right? To do bigger things, but that is the reality right now. So we're doing what we can with what we have, but we're still grateful for what we can do, okay? Because still it's more than what any other country in the world can do in astrophysics. Well, any other questions? If not, I'm gonna say thank you very much for this invitation, gave me an opportunity to talk to. I love to go to places and talk to younger individuals, you know, early career professors and students, because that provides a lot of energy, a lot of ideas, okay? I don't get that talking from my home here, but still, hopefully you get some of the excitement of what we're doing here.
Yes, it was a very nice talk, and we did get a lot of the excitement of NASA's achievements, and there's a lot of great interest in things to come.
Yes.
So thank you.
Thank you very much. Thank you for inviting me.
All right, everyone. Thank you for attending.
And if anyone want to contact me, my name is Mario.Perez. My last name at nasa.gov. Very simple. If not, you Google me, you're going to find the email. Okay. Thank you.
All right. Thanks a lot.
Thank you very much.
Bye, everyone. Thanks for attending.
Bye.